So today we're going to look at radical and rational functions and an introduction to the types of functions and applying transformations to them. So first we're going to look at a radical function. So a radical function is any function that involves a radical sign and a variable inside of the radical sign. So this one here is just going to be y equals root x, the most basic function. We can look at a table of values for this. And we know that when we plug in 0, the output is going to be 0 as well. When we plug in 1, our output is going to be 1. So we do have these nice points here. When we plug in 4, we're going to get 2. And if we plug in 9, we will get 3 in this case. So the basic function looks like so. Now the domain and the range. The domain, we're going to have all the values that are going to be greater than or equal to the value that makes it non-negative inside of the radicand. So we're looking at this case everything greater than or equal to 0, and it can be all real values above that. The domain and the range. The range is then going to be based again also on this lowest value. It's either going to be above or below if it's reflected. So in this case, y is going to be greater than or equal to 0 for all of these cases here for the range. Now, just like transformations in other units that we've done, we can reflect the graph over the x-axis or the y-axis. We can vertically expand or compress it. We can horizontally expand or compress it. And we can vertically and horizontally shift the graph. So we can actually write any of these functions so that we can have an a on the outside, a b on the inside, an x minus c on the inside, and a d on the outside. So again, a is going to be your reflection if it's negative, as well as a vertical expansion or compression. Your b is going to become again the reciprocal of b for the horizontal compression expansion. Again, if it's a negative, then you'll have the reflection as well. The c will be your horizontal translation, and then your d will be your vertical translation. Now the one thing you're going to want to look for is how these transformations affect the domain and the range. So when you're looking at a horizontal compression or expansion, your lowest point will stay here. It will stay at the initial point because it's on the y-axis and the x-axis. But the horizontal translations are what's going to move that point, the starting point, to a new point on the graph. Same thing with the vertical one as well. The vertical expansions, compressions, the minimum point here is going to stay where it is, but as soon as we start translating, it's going to actually move where the y value will end up. So looking at those are important when we're looking at domain and range. And again, remembering you need to factor here. So you need to have your b factored out, so that way you can easily see what your translations are for the horizontal aspects. So the next type of function we're going to look at rational functions, and the most basic one is a reciprocal function. So when you have a rational function, it actually can be any polynomial divided by any polynomial. In this case here, I have y is equal to 1 over x, the very most basic one, but any rational function can be written as any polynomial over a polynomial. So when we're talking about that, there are, again, we know non-permissibles. So in this case here, x cannot be equal to 0, which also aligns with the asymptote of the graph, like so. When we're talking about any rational function, that means this polynomial on the bottom cannot equal to 0. So we do have to consider factoring it and looking at possibly multiple asymptotes depending on how it factors. When we also look at a basic reciprocal graph, 1 over 1 is always going to become 1, and same with 1 over negative 1 will always become negative 1. So we do have some key points again. If we also were to rearrange this equation, try to isolate for x, we can also see that if I times both sides by x and then divide by y, y will end up on the denominator. So as a result as well, we do also have a horizontal asymptote, in this case here, as it gets closer and closer to 0, it won't actually touch. So we also know that for the domain and the range, as a result, that these two values are very important. X can't equal to 0 because you have an asymptote for the domain, and also for the range, y can't equal to 0. So those are some key things to notice as well. So we're going to look at transformations again to a basic reciprocal graph first, and then we're going to look at how we can introduce larger degree polynomials over polynomials and see how that affects the graphs as well. So similar idea, when we have any function, I'll actually erase that and put a function there. When we have any function, so function notation, of we'll do a basic reciprocal graph. Technically, we can have a vertical expansion, compression, reflection as well. You would have a possible horizontal compression, expansion, and a horizontal shift, and a vertical shift as well. So we could write it like this to start with, but most people actually can see that a times 1 is just going to become a over bx minus c plus d. So the key things are, again, because our denominator is where our variable is, anything that will change the horizontal will have to happen under the denominator. So your b value and your c value are here factored again on your denominator, and the a and the d are technically happening to the vertical components of the function. So a is technically outside of here, but we do write it as a numerator to make it a little bit simpler, and we write plus d on the side. Now, you could even go one step further and find a common denominator for this, because d is technically outside of here. So d could get multiplied by this common denominator and be written as part of the numerator. So that is something to consider as well. You may see them in different formats, but if you can always extract it into this sort of format, you can then see what's happening to the basic reciprocal graph by having your d outside of here. So you could have a more complicated view where it's going to become a plus d times your common denominator all over your common denominator. Most likely you'll see it in this format here, but there is a chance you could see something like this as well. Okay, so now let's take an example of doing transformations on the basic graph of root x. So I want you to graph the 3 times the function of negative x minus 2 plus 1. So first we need to be able to identify what sort of transformations have happened to our base function in the square root here, and then apply it to the graph. So you can leave it in function notation if you wish, and then write down how the points correlate. You can translate it into a square root equation if that helps you as well. So I'll show you a couple of different things you can look at, but ultimately we need to figure out what is happening here. So first things first, and I've done this on purpose, is I've included something that you need to factor out, because you have to factor in here any coefficient. So that way it's very clear what the horizontal compressions, expansions are, or reflections are, so they are isolated. So in this case there is a negative sign outside of this, so I am going to factor out negative 1, and that then leaves me with x plus 2 inside of the brackets. So now I can identify that I have a vertical expansion by 3. I have a reflection here. So because it's with the x right here, your x's will switch to the other side of the y-axis, so it's a reflection over the y-axis. We have our plus 2 here, so technically it is a horizontal translation, and we're going to be going left 2. And then we have a vertical translation, and then that will be going up 1. So again, order of operation is important. You need to make sure that you are going with a multiplication and division. So basically expansions, compressions, and reflections first, and then we do the horizontal and vertical translations second. So again, identify your key points that we know work nicely. So we'll use those 4 points that I've identified. We're going to vertically expand them all by 3 and then reflect over the y-axis. So 0 multiplied by 3 is going to stay at 0 and reflected is going to stay exactly where it is. Your 1 is going to end up at 3 and then reflected over the y-axis, so we're going to have a point here. So I'm just going to connect these so we can see. 4 is going to give us 2. 2 times 3 is going to be up here at 6. And we'll put that over here. Sorry, over a few more spots. So 6. There's my 4. Okay, so I'm here. And then my 9 at 3 is going to become 9, which is just going to be at the end of my grid here, so up here. And then it shall carry on. Okay, so there is my vertical expansion, my reflection over the y-axis. My next step is then I have to go left 2 and up 1. So if I go left 2, up 1, I will get this point here. Left 2, up 1, left 2, up 1, and I will be off the grid for that one. Now again, remember I said you need to know your starting point. So here is, oops, it's going to go off the grid over here approximately. There we go. And it's going to keep going. So for my domain and my range now for this graph, we can see that the domain is not going to be strictly greater than or equal to 0 anymore. It's actually going to be less than or equal to -2. And it's going to be all other real values. My range is still going to be in the positive because there was no reflection over the x-axis. And it's going to be from the point of 1 and greater. So y is going to have to be greater than or equal to 1 in all real values. Now if you wish to look at it in terms of how it looks inside of a square root, just for being able to view it rather than in function notation, we would then have this function here where you'd have the 3 on the outside, square root, negative x plus 2 inside the square root plus 1. That would be the equation in a square root format, or you could look at it in function notation format. Either way, you would still isolate the same vertical expansions, the negative reflection, horizontal translation, and the up one. Okay, so now let's look at a reciprocal function and what it looks like when we work with it in this notation. So again, identifying what we have here. First little bit here, we have a -2 outside of our function. The -2, again, is going to have a reflection and also a vertical expansion. And you're going to reflect over the x-axis. We also have, in this case, a horizontal shift to the right, 3. And we also have a vertical shift, and we're going to go up 4. So some of the key things you need to watch on this one are where the asymptotes start and where they end off. So you do need to identify where they are. They will also help you see where the graph should be trapped between. So what axes they're technically trapped in between. So the reflection is not going to affect either the asymptotes. The vertical expansion is not going to reflect or affect any of the asymptotes. What affects the asymptotes are the shifts up and to the right. So if we look at our asymptote here on the y-axis, it's going to go 3 to the right. So we will need to have that there. That will be where our new vertical asymptote is, and our horizontal asymptote is going to go up 4. So this is the area that we are now working with. We will have a portion in the quadrants that we've now made. So let's take a look at how the points change. So again, let's look at the key points of 1s and -1s, because those are nice ones to work with. So if we do a reflect over the x-axis and a vertical expansion by 2, it's going to expand it up to 2 and then reflect over the x-axis to -2. So we will have a point here And if we do the same thing with this one, it's going to go to -2 and then reflect, so it becomes +2. So we can see it switch the quadrants that they're in based on the original graph. It's going to be doing this before we move it. And then using these two key points, we can then shift it right 3 and up 4. So let me just change the color so it's a little bit easier to see. So here, from this point here, we're going to go right 3, 1, 2, 3, and up 4, 1, 2, 3, 4. That will be our vertically expanded point that correlates to this point here. Then we're going to use this point here, same thing, we're going to go right 3, so 1, 2, 3, and we're going to go up 4, 1, 2, 3, 4, so we're there. Now again, having those asymptotes to show where it's trapped in between will help us a fair bit. The point that was at a half, right, that would be this point here, gets expanded by 2, it goes to 1, because a half times 2, and then reflected, so we should have another point that's here as well. So if you wish to have a secondary point, we'll have the same thing happening on both sides. So we should have this point here as well as this point here. That will help you kind of see how it's trapped in between, how it's been vertically expanded. So having an extra point and also having the asymptotes to guide where it is trapped in between will help you as well. Now in terms of how that looks in a function, if we were to write it in this format, our new function would be -2 over the top here. We would then have x minus 3 on the denominator and then plus 4. Now this one shows us quite nicely. There's my vertical expansion of 2 and my reflection. This is showing me I'm going right 3, and this is showing me the function's going up 4 for the y values. Now in the case that they actually did write this out as something written over a common denominator, you would then have -2 plus 4 times x minus 3 all over x minus 3. This would then simplify down to -2 plus 4x minus 12 all over x minus 3. And now we're looking at an equation that looks like this. Sorry, one second here, close that down. Why it was open, I'm not sure. Then we have 4x minus 14 all over x minus 3. So you may see something in this format and be like, oh boy, how do I work with this? Well, you also need to look at what's happening with this function. So a couple of little analysis aspects that could help you. We know our vertical asymptotes and our horizontal asymptotes are based on basically what's happening on this denominator here. So this tells me automatically that x can't equal 3, which means I have a asymptote here at x equals to 3, which we do. We also can see that if we were to rearrange this and isolate for x, we would then be able to figure out this one here. So that is another way of looking at it too, to see what would happen if we were just trying to isolate for x. So we could times both sides by this, and then you'd have to also work with the splitting of the numerator and denominator to isolate for x, which is a little bit trickier, but there is a nice little trick which I want to show you. So we know that the asymptote is here at 4. We also have the same degree with our numerator and our denominator. So one of the nice little tricks is if they are the same degree and we were to divide the two out, we actually get the value of 4. 4 divided by 1, so you're going to get 4, which happens to be our horizontal asymptote. Now this only works when they are the same degree, but that is a nice way of finding a nice, easy horizontal asymptote without having to rearrange the whole entire equation. So that's another way of looking at it too, and then you can use a table of values to figure out a couple of the values that go inside of the graph. That would then help you show the shape of the graph. So I hope that helps you get started. We are going to spend a little bit more time on this sort of polynomial over polynomial scenario, which will help you figure out some key points, domain and range. Again, for domain and range on this one, it's based on your non-permissibles, so domain is going to be everything except for 3, and the range is going to be everything except for 4. We will be looking at more throughout this unit, but this is just an introduction, so hopefully that gets you started.